So this integral here is extraordinary, just as the method that I want to use in order to evaluate it. So first of all, I'd like to call this guy here I, just for, reference purposes. Now, notice that all the stuff in the integral is an even function. I mean, cosine is even, x squared plus 1 is even, it's all even, awesome. I can just write this integral as 2 times the integral on half of this interval, of half of the original interval. So times the integral of the same integrand but on the bounds of 0 and infinity. Lovely. Now, I'd like to introduce the parameter t to this integral. I'd like to make this integral a function of the parameter t, but where do I place the parameter? Well, I'd like to place it in, let's say, the most obvious place possible, the most intuitive place possible. I like to say it. I know what's going on here, but not everyone has to. Yeah, it's funny. So I'm gonna place it inside of the cosine function, multiply the variable x by that parameter. So what we really care about here, I mean, the integral we're looking for, the original I, is our function I of t evaluated at 1 and multiplied by 2 because, well, we performed that odd-even trick with the interval at the very beginning. Awesome. So now what I'd like to do here is the inverse Feynman trick, which is integrating under the integral sign. I love it. Is the Laplace transform. I'd like to take the Laplace transform of this integrand, of this integral function I of t, which will give me the integral from 0 to infinity of e to the negative st times this function I of t, which is just the integral that we're looking for there, yeah? It's gonna be all dt as well. But now, the next thing is that e to the negative st is, well, 100% independent of x, so I can just slip it inside of the integral. Yeah, well, that's nice, but, I don't really like the order that I'm integrating stuff in here, in this double integral. I'd love to be able to just, switch dx and dt places, yeah? So I'd like to make the dx go away to the right and make the dt come to the left a little bit. Can I do it? I can. There is a thing called Feynman's theorem, which tells us that we can change the order of integration whenever the stuff that we've got inside of the double integral is going to be convergent on this interval, and well, it will be convergent. I mean, we've got e to the negative exponential, yes, so negative exponential, which will drag down to 0 as hell. That cosine of t times x, well, this thing will oscillate, and x squared is going to drag it down to 0 as well. No problem with continuity either. Awesome, let's roll. Let's switch the order of integration there, and let's just, well, kind of notice now that we're integrating with respect to t here, so this 1 over x squared plus 1 is a constant. I can take it out of this integral, just like this, and well, now, love it, what I've got inside of this integral with respect to t, that's just the Laplace transform of cosine of t times x, which is s over s squared plus x squared, and I love it. I can just plug it into my function now, and I've got this integral from 0 to infinity of those two fractions that I multiply together. And well, it is still quite messy, but I can use partial fractions to deal with it, and I will do it right now, but because it's boring as hell, I'm gonna just skip it and, well, give you the answer right now. You can verify it for yourself if you want. And you know what? The nice thing is that I can just integrate this thing right now. I'm gonna get that the Laplace transform of my integral function I of t is equal to s over s squared minus 1 times those two arctangents in the bounds of 0 and infinity. Both arctangents, when given a 0, give 0, and when given infinity, they spit out pi by 2. They are inverse tangent functions, yeah? So we'll get this pi by 2 that we can just take in front of the entire expression, and then s over s squared minus 1 times, and I'll just write this thing here as, well, s minus 1 over s. Those s's and s minus 1 cancel out. We'll get pi by 2 times 1 over s plus 1 as the Laplace transform of our integral function I of t. And now to recover our function we really just care about, the I of t, no problem in doing that. Just use the inverse Laplace transform. Look at your table of Laplace transforms there. And you'll get e to the negative t. And so I of t, our integral function, is pi by 2 multiplied by e to the negative t power. And so this double I of 1, which we care about because it's our original integral we're looking for from the very beginning, is pi by 2 times e to the negative first power times 2. That's pi by e. I love this result. I mean, I just love it. Hope you guys enjoyed it and see you in the next one. Bye.